Hello, class. Wow. Wow. Wait about 1 more minute, then I'm going to get started. You can watch me shove this bread into my face. Okay. I think I'm going to get started. Hello, class. This is going to be a short lesson today. And so my goal is to finish this lesson early, go into the Zoom room and check in with you guys, and then I will let you go pretty early today because I assigned that midterm, and the midterm is going to take, an hour or two outside of class, so I want to give you back that time. I don't want to, so I'll keep my class short. So, what are we going to talk about today? Well, the first thing we're going to talk about is something called power. Okay, which is denoted by P. Okay, and power is equal to the energy consumed or produced so we could talk about the power output of something or the power consumption of something. So if it's producing energy, it's a power output. If it's consuming energy, it's power consumption. Divided by the time it took to produce or consume that energy. Okay, so we could also think about it as the rate of energy production / consumption. All right, so if I wanted to just write this more briefly, I could say power is energy per time. All right. And then that allows us to get the units of power. So the units of power are going to be units of energy divided by units of time. So the units of energy are joules, and the units of time are seconds. So power is measured in joules per second. Now there's a more common, it's pretty rare that you see joules per second, okay? What you're more likely to see is the watt, W. So 1 watt is equal to 1 joule per second of energy use. So if you have a light bulb and you look at the light bulb on the box of the light bulb, if it's an incandescent light bulb, it might say something like 60 watts. So meaning that when you plug that light bulb in, it's going to consume 60 joules per second of energy to give you that light, okay? If you talk about something like a wind turbine might produce 1 megawatt, so 1 million watts, which is 1 million joules per second. All right, so you can consume the power or you can produce it. By the way, LED bulbs are much more efficient, so they might only be 10 watts for an LED bulb or even less, okay? So they're much more efficient at converting electrical energy into light waves. Another common unit of power output that you will see in any type of engine application is the horsepower. And 1 horsepower is, don't quote me on this, it's like 746 watts, I want to say. It's 740 something. I can't remember if it's 742 or 746. So 740-ish watts is 1 horsepower. So you will see that on engines. So for example, a couple of lessons ago, I was talking about boats and how my family had a boat when I was growing up, and that boat had 250 horsepower engines. So that's telling us the power output of those engines. Okay, so we're going to talk more about power later on in this class because we haven't really touched on it yet, but I just wanted to introduce it because we need it for the content that I actually wanted to teach today, which is called intensity. So the intensity of waves. And the intensity of waves is a measure of the energy carried by a wave. I should say it's kind of a measure of the concentration of energy carried by a wave. Okay, how condensed is that energy, or is it spread out over a large volume? So what we want to think about is, let's suppose you have a source of a wave. Okay, so this source is emitting waves in all directions. Okay. And let's imagine that we have a wall. So I will try to draw the wall in like a 3D perspective. Okay. So it's a wall, it has a certain width and it has a certain height. Okay. And it is basically absorbing the power, some energy per time from the source of the wave. Okay, so the source is sending out waves, and some of those waves are hitting this wall and being absorbed by the wall. Okay, so the intensity which is denoted by I, is equal to the power absorbed by the wall, and I'm going to say the target, actually. We can think about it like a target, divided by the area of the target. Okay? So see how it's per area. It's per area. So that's why I say it's like a concentration. Okay? So if you have the same power absorbed by a smaller area, then that energy is more concentrated into a smaller space. Okay? So the smaller the area is for a given power, the higher the intensity. So I will often write this just as intensity is power divided by area. And this equation allows us to get the units of intensity, which would be units of power divided by units of area. So that would be watts per square meter are the units of intensity. All right. So let's do a little example here. Let's consider a 1.5 meter by 2 meter wall that is absorbing 900 joules of energy each minute. Okay. What is the intensity? Okay, so first let's figure out the power. So the power absorbed, remember, power is not the same thing as energy. It's the rate of energy consumption. So it's energy per time. So we're absorbing 900 joules in 1 minute. Now, one minute is not a standard unit of time, so we want to convert that to seconds instead. And so this gives us 15 watts is the rate of energy absorption. Okay. And then the area, it's a rectangular wall, so it's 1.5 times 2, width times height, which is 3 square meters. Okay. So then the intensity is going to be power per area, which would be 15 watts in 3 square meters, which is 5 watts per square meter. Okay. So so you could think about intensity of a sound wave as being synonymous with its volume. You could think about intensity of a light wave as also being synonymous with its brightness. So another common unit of intensity is decibels. If you're talking about sound waves, how many decibels is the wave carrying? Okay, so that's also a measure of intensity. All right, so now that we know what intensity is, I want to talk about how does intensity vary with distance from the source of the wave. Okay, so you have, oops, that wasn't even, sorry about that. So you have some source, and the source is emitting waves in all directions. So the wave is traveling out in all directions like that. Now, the general idea is because waves are traveling away from the source, as the waves travel away from the source, they're getting less and less concentrated because they're spreading out into a bigger region of space, okay? So the waves are spreading out. And remember, intensity is like the concentration of energy that a wave is carrying, okay? So as the wave spreads, its intensity drops, okay? So the intensity decreases as you get further away. All right. And so there's a really nice formula that summarizes that. It says that the intensity is power divided by 4 pi r squared, where P is the power output of the source, and R is the distance from the source. Okay, so we can see that distance from the source is in the denominator, and so as you get further away, the distance from the source increases, and so the denominator gets bigger, and the intensity drops. So the further you are away from the source, the less intense the waves are. Now, this is making an important assumption. It's assuming the source is, and I'm going to use a fancy physics word, which is isotropic. So isotropic means that the waves are being emitted equally in all directions. Okay. So isotropic means the same in every direction. So for example, if I'm speaking, my mouth is a source of waves, of sound waves. That is not an isotropic source because my mouth is emitting more waves in the forward direction than it is behind, right? If I'm facing you, you can hear me more easily because the intensity is greater in the forward direction versus the reverse direction, okay? You know, radio antennas can also have this kind of a beaming capability. They call it beaming. And you can have an antenna that looks like a radar dish that is sending waves in a specific direction more than other directions, okay? So those are non-isotropic sources of waves. Another good example of a non-isotropic source is a laser, okay? The laser beam is all in the forward direction and basically nothing in any other direction. So lasers are very non-isotropic. But there are other sources of waves that are isotropic. A great example is the sun. The sun equally emits light in every direction, okay? So we would say that it is an isotropic source. Another good example is, oh, hello, Ivan. Hello, Ivan kitty. Meow. Meow. Hello, Ivan Kitty. Another good example of an isotropic source is a like a tsunami siren. Okay. Sorry, Ivan is demanding pets here. And tsunami sirens are designed to be heard by everyone in the vicinity. So they have basically speakers that are pointing in every single direction so that, it's emitting the sound equally in every direction so that you know to get away from the ocean if a tsunami is coming. Okay, so let's do an example of using this formula. The sun has a power output of 3.8 times 10 to the 26th watts. So that is an incredible amount of energy, okay? That's 100 million billion joules of energy per second are leaving the sun in the form of light waves, okay? Huge amount of waves, okay? But what happens is the further you get away from the sun, those waves are spreading out. And so the intensity starts to drop as you get further away from the sun. So we, on Earth, are 1.5 times 10 to the 11th meters away from the sun. Okay, so what is the intensity of sunlight at Earth? Okay, so we just use the equation directly. Intensity is power over 4 pi r squared. So the power is 3.8 times 10 to the 26th watts divided by 4 pi, and then our distance from the sun is 1.5 times 10 to the 11th. Got to square that. So I did this problem last period, so I already know the answer is 1,350 watts per square meter. Okay. Now this is kind of interesting because this is basically what the intensity of sunlight is in space, but we are not in space directly above the Earth's atmosphere. Okay, but we are not in space. We're below the Earth's atmosphere. So as the sunlight is traveling down through the atmosphere to us on the surface, some of that sunlight is being absorbed by the atmosphere, which reduces the intensity. So the energy received at the surface is less. Okay, so it's only about 1,000 watts per meter squared at the surface. Okay. And then if we wanted to use that energy, for example, what if we wanted to harvest that luminous energy in a solar panel? Okay. Well, it turns out that solar panels are about 10% efficient. So what that means is that you're only going to be able to use 10% of that. And so solar panels have a power output of about 100 watts per meter squared. All right. So if you have a solar panel that's 1 meter by 1 meter, okay, it's going to produce around 100 watts, maybe a little more, depending on the efficiency. And of course, that also depends on the time of day. Is the sun directly overhead, or is it at an angle? And it depends on the weather. Is the solar panel clean, etc. So yeah, so now this type of calculation was actually used by NASA all the time. They use this this formula all the time when talking about light waves. So, for example, when we put a rover on Mars, they have solar panels on them that provide some power. Okay. Usually, okay, so solar panels provide power, but because, for example, Mars is further away from the sun, a solar panel on Mars is not going to produce as much power as a solar panel on Earth because the intensity of sunlight is less at Mars. Okay? And if you have something that goes out even further, then solar panels aren't even all that useful anymore. Okay? Because you're so far away from the sun that the intensity isn't enough to really power anything. And so a space probe that's going way out there is going to have inside it a radioactive source, like plutonium, for example. And the heat generated by the plutonium is what's going to power the probe instead of solar panels. Okay. The converse is if you go closer to the sun, solar panels are more effective, right? Because we're getting closer, so the intensity is higher. All right, so there's one last part here. How did I get 1,000? So, yeah, I'm just saying that there's a question in the chat that says, how did I get 1,000 on the surface? That's taking into account atmospheric absorption of some of this energy. Okay, so there was no way to calculate that this would be 1,000. Okay, I'm just saying that this is what it is if you are in outer space above the atmosphere, and this is what it is below. Okay, but there's no way that we could calculate that it would be this, because without knowing the exact composition of the atmosphere. Okay, so the next question I want to ask is, how does the intensity vary with the amplitude of the waves? And I think this part is probably fairly obvious. The bigger the wave, the more intensity. Okay? So if you have a larger amplitude for the waves, that means more intensity. So in fact, there's a nice little formula here. So the final intensity is equal to the initial intensity times the final amplitude divided by the initial amplitude squared. So, and I want to point out that this capital A stands for amplitude, not area, because we already had an A earlier in the lesson right here. So this A stands for area, this A stands for amplitude, okay? So we can see that the bigger the amplitude is, the bigger the final amplitude is compared to the initial amplitude, the more the intensity is going to increase. So let's do an example. What happens to the intensity if you double the amplitude? Okay. So if you were to double the amplitude, then that means that the final amplitude is twice the initial amplitude. All right? Which means that A final over A initial is 2, which means that A final squared, A final over A initial squared is 4. So keep in mind that there's this square here. So that says that the final intensity is 4 times the initial intensity. So doubling the amplitude results in a more than double increase in the intensity. It results in a 4-time multiplier on the intensity. Okay. Similarly, if you were to triple the amplitude, it would be 9 times the intensity. If you were to quadruple the intensity, it would be 16 times the intensity. So you square that to get the multiplier for the intensity. So amplitude greatly increases the intensity of a wave, just like distance from the source decreases it. All right, so that is my lesson for today, and I will see you in the Zoom room for a quick check-in.